So let's start the next lecture on stoichiometry. Stoichiometry. So what is stoichiometry, and let's discuss what does it entail. So in this lecture we are going to talk about what the definition of the mole and how to determine the formula of an unknown compound and how to write and balance the chemical equations. And in the second part of the lecture we'll talk about calculating the quantities of reactant and the product, and finally complete with the fundamentals of solution stoichiometry. So let's start with the mole. So we already discussed the definition of mole when we discussed the atomic unit, but we'll discuss it much more clearly here. So mole is the amount of substance that contains a small number of entities, as there are atoms in exactly 12 grams of carbon 12. So we are exactly looking for how many entities are there. So the term entities can refer to atoms, ions, or molecules. Can also be formula units if you have an ionic compound. It can be electrons if you have a single atom, and if you have a metal, and in fact it can be any type of particle. So 1 mole contains about 6.022 times 10 to the power 23 entities. So this is the number of particles in a single mole of a substance. So this is given to 4 significant figures. So this number here that you get here is called the Avogadro number and is abbreviated by the symbol N. Right? So whenever you see N here, so N refers to 6.022 times 10 to the power 23 per mole. So this is the definition for the Avogadro number. So any entity with 1 mole of a quantity contains about 6.022 into 10 power 23 entities. So some of those familiar substances, for example, you can take a look at copper here. So this is 1 mole of copper. This is 1 mole of a solution. This is 1 mole of salt, and this is 1 mole of sugar, and this is 1 mole of aluminium. So these are elements that you can see. Notice that even though the quantities are different, the actual quantity that they refer to is exactly the same. So this is a standard that we use that generally refers to 1 mole of a substance. So next, let's talk about the molar mass. So we talked about molecular mass and atomic mass in the last lecture. So let's talk now about the molar mass. So the molar mass is the mass per mole of its entities. So mass of 1 mole of a substance is basically called as the molar mass. So the name itself gives you the definition. So for monoatomic elements, so the molar mass is the same as the atomic mass, but in gram per mole. So for example, if you take neon, so neon has an atomic mass of 20.18 U. So when you want to calculate the molar mass, so the molar mass of neon is exactly the same amount, but in place of U we write gram per mole. So this is the definition that we use. So the atomic mass and the molar mass, the value is the same, the unit is what differs in the value. So it can be simply read from the periodic table directly as well. So even the molar mass can be read directly from the periodic table. If you have molecular elements and for compounds, the formula needed to determine the molar mass is similar to that of the molecular mass. So molar mass here, again we calculate 2 times the molar mass of each individual element. For example, if you take oxygen, we are taking twice the amount of individual quantity of oxygen, so that's 2 times 16, and we change the units to gram per mole. In the same way, SO2, we write 1 times the molar mass of sulfur into 2 times plus 2 times the molar mass of oxygen, and that gives you 32 plus 32, that's 64 gram per mole. So remember the units, really important, gram per mole. Now, so when you take the exact quantities of a substance, if you take glucose, in glucose you have 6 atoms, 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. In terms of the moles of substance, there is 6 moles of atoms of carbon, there is 12 moles of hydrogen, and there is 6 moles of oxygen. And when you want to calculate the exact number of atoms inside them, then we can calculate it by multiplying the mole with the Avogadro number. So multiply the mole with Avogadro number, that's when you get the total number of atoms. When you want to calculate the mass of the molecule of the compound, we can calculate it with the atomic mass unit, but mass per mole can be calculated as grams. So that's the only difference between the other quantities and here. So now when you want to calculate the mass, you can multiply the number of moles of the quantity with the number of grams of the substance. So number of moles is determined by these, generally given by the representation n, small n. So n is given as mass by molar mass. So the number of moles is given by mass by the molar mass. The number of moles of a quantity is given by mass by molar mass. If you want to consider the number of molecules, so multiply the number of moles with the Avogadro number. So that's where you get the number of molecules. And if you have the number of molecules and you want to calculate the number of moles, then we can calculate it by reversing the formula. So n becomes the number of entities over the Avogadro number. So these are the common formulas that we're going to end up using in this chapter. So make sure that you review these formulas just so that you remember. And main formula to remember is the number of moles is mass by molar mass. So this is the main formula to remember. Now, so how do you mass mole relationships for elements change? So when you want to convert mass into moles, so we basically convert it by calculating, by multiplying it with the molar mass. So when you want to convert it into the number of moles of the substance, so divide it by the molar mass. So mass by molar mass gives you the number of moles. Now multiplying that number of moles with the Avogadro number gives you the number of actual entities or the atoms or molecules in that substance. So this is the idea behind the mass mole number relationship for elements. Let's take a simple example. So let's take a simple example here. So here they have given us silver is used in jewelry and tableware but no longer in US coins. How many grams of silver are in 0.342 mole of silver? Now remember the formula, the number of moles is mass by molar mass. So they are asking us how many grams of silver is there. So grams, remember that mass is represented by grams, molar mass is represented by gram per mole. So now mass can be written as mass becomes number of moles into the molar mass. The number of moles is given in this problem, which is 0.0342 mole. So it becomes 0.0342 mole. But we do not know the molar mass, so we need the molar mass of silver. So how do you find the molar mass of silver? So from the periodic table. So let's look at the periodic table. So let's take a look at the periodic table. So from the periodic table, we want to find Ag. So where do you get Ag here? So you have Ag right here. So the value is given as 107.9. So let's use the value there. So that is 107.9. Remember, this is the molar mass, which means you write it as gram per mole. So this is 107.9 gram per mole. So when you actually take out the units, you still get the same unit, gram. So now you want to find the value. So that is 0.0342 times 107.9. So that gives you a value of 3.69018 grams. But remember the significant figures. We'll have to count the number of significant figures in the problem. So here the total number of the highest number of significant figures is 4. So we have to use 4 significant figures. So when you want to use 4 significant figures, so we have to eliminate the last 2. So write it as 3.690 gram. So this is the mass of silver that is present in 0.0342 mole of silver. So this is how you can convert from one unit, one system into another. So let's try another problem. So here they have given you the problem here. So gallium is a key element in the solar panels, calculators, and other light sensitive electronic devices. So how many gallium atoms are present in 2.85 into 10 power negative 3 mole of gallium? So let's take a look at this problem. So the total number of moles N is given as 2.85 into 10 power negative 3 mole of gallium. So they are asking you to find the total number of gallium atoms. So remember the formula, total number of gallium atoms can be found as multiplying the number of moles with the Avogadro number. So the number of moles is 2.85 into 10 power negative 3 times the number of the Avogadro number is 6.022 into 10 to the power 23. So find the value. So if you multiply 2.85 with 6.022, that gives you a value of 17.1627. But notice that the maximum number of significant figures you can have is 3. So round it off now. So when you round off this, you get 3 here. So when you round off 3, you get 3 when you round it off, you get 6 here. So 6 when you round it off, this becomes 2. So the value should be 17.2 into 10 to the power. Now this is 10 power negative 3 and 10 power 23. So you get 10 power 20. Now push this number one side this way, so you get 1.72 into 10 power 21. So if you want to do it, if you don't want to do it manually, you can try doing it by using a calculator. So now this gives you the final answer. This is the number of atoms in this many moles of gallium. So this is the number of gallium atoms. So remember the formulas. I'm going to write them again. So the number of moles N is given by mass small m over the molar mass uppercase M. So mass is in grams and molar mass is in gram per mole. So remember the formulas. The other one is the number of entities. So remember that whenever you change the term entities, you can use it as atoms, formula mass, formula quantities, or you can use it as compounds as well. So the number of entities is the number of moles N times the Avogadro number. So which is uppercase M. The value is 6.022 into 10 power 23 per mole. So remember these two formulas. So if you remember these two formulas, the entire first part of this chapter becomes easier. So let's try another problem. Here you have iron, which is the main component of steel, is therefore the most essential metal in society. So it's also essential for the body. So they're asking you how many iron atoms are in 95.8 grams of iron. Now pause the video right here and try to solve this problem. Notice that they are asking two processes. So the plan here is to start converting mass. So the mass is given 95.8 grams. So you are finding the number of moles first. So the number of moles is mass by molar mass. So first calculate using the periodic table, calculate the actual molar mass. So for your convenience, I'm going to write down the value. So the molar mass of iron is 55.85 gram per mole. Now once you calculate the number of moles, they are asking you for number of iron atoms. So the number of iron atoms becomes the number of moles into the Avogadro number. So pause the video right here and try to solve this problem. Next, let's talk about amount mass number relationships for compounds. So what do you do when you have a compound rather than having a single entity or a single element? So let's take a simple example. So here we have a problem. So nitrogen dioxide is a component of urban smog that forms the gases in car exhaust. How many molecules in how many molecules are in 8.92 grams of nitrogen dioxide. So let me try this one. So the mass is given here is 8.92 grams. Remember nitrogen dioxide, how to name it? Nitrogen is N, dioxide, so notice that di here, the di represents that there are two of them, so nitrogen dioxide, NO2. Now we know the mass, now we want to find the molar mass, so the molar mass of NO2. So molar mass of NO2 becomes, so 1 times the molar mass of nitrogen plus 2 times the molar mass of oxygen. So 1 times, so the molar mass of nitrogen is 14.01, so from the periodic table. So remember that these values I am writing are from the periodic table. So the molar mass of oxygen is 16.00. So you have 14.01 plus 32. So 14.01 plus 32 gives you 46.01 gram per mole. Remember the units, never forget the units for molar mass. Molar mass always gram per mole. Now remember the part here, they are asking you for the number of molecules that are there, which means you have to first find the number of moles. The number of moles is mass by molar mass. Mass is 8.92 over molar mass is 46.01. So 8.92 over 46.01. That gives you a value of 0.194. So notice that there are three significant figures that maximum you have to have. So 194 mole. So this is the number of moles of the substance that you have. Now once we found the number of moles, the next one we want to know is the number of molecules. So the number of NO2 molecules can be given by the formula, the number of moles times the Avogadro number. So the number of moles is 0.194 moles of NO2 times 6.022 into 10 power 23 NO2 molecules in how much? 1 mole of NO2. So molecules per mole. So mole and mole gone. So you have 0.194 into 6.022 into 10 power 23 NO2 molecules. So by using a calculator, so that gives you a value of 1.17 into 10 to the power of 23 NO2 molecules. So this is the number of NO2 molecules in 8.92 grams of NO2. So 8.92 grams of NO2 contains 1.17 times 10 to the power 23 number of NO2 molecules. So now solve this problem now, and they are also asking you how many oxygen atoms are there here. So this brings up the question, what is ammonium carbonate? So if you remember the name, carbonate is CO3 and ammonium is NH4. Alright. So if you remember that both the charges is NH4 is plus, so CO3 is 2 minus and NH4 is plus. So shift the charges in the opposite direction. So you have NH4 taken twice CO3. So when you want to calculate the number of the first one is the number of formula units of NH4, so that directly you can calculate it from the mass just by the last method. Now I want to do the last one, which is B part. So B part asks you for number of oxygen atoms. Notice that in each formula unit of ammonium carbonate there is 3 oxygens. Use this ratio, which means that 1 mole of NH4CO3 contains 3 moles of oxygen, which means that whatever the number of molecules that you end up with, oxygen will be 3 times that number of molecules. So remember the ratio here, 1:3 is the ratio, so which means the molecules also will have the same ratio. So each formula unit has 3 oxygens, so 1 mole will contain 3 moles of oxygen. So whatever the number of molecules that you end up with as the answer in the first part will be, so they multiply 3 to it, that will be the number of oxygen atoms in the sample. So pause the video right here and try to solve this problem. Next, let's discuss the mass percent from the chemical formula. So every element will contain a certain amount that it contributes to the chemical formula. So that is what we are going to calculate as the percentage. So mass percentage, when you have an atomic mass, it will be atoms of the molecule, atoms of the number of atoms of a particular element in the formula times the atomic mass divided by the molecular mass of the compound. And when you want to have a mole, so the number of moles of the element in the formula times the molar mass of X divided by the mass of 1 mole of the compound. Now let's take a simple example and let's try to see if we can find out each of these mass from the values. So glucose is a key nutrient for generating chemical potential energy in biological systems. What is the mass percent of each element in glucose? So I'll be using the second formula because it's much easier. We don't want to confuse atomic mass and molar mass. So I'm going to use the second one. Now let's take the glucose here. So glucose is C6H12O6. So for our understanding, let's consider that there is 1 mole of glucose. So let's consider the 1 mole of glucose. So remember, from the formula we are finding the mass percent of 3 elements. So we are finding the 3 elements here. The 3 elements are, one is carbon, the other is hydrogen, the last one is oxygen. So there are 6 carbons, 12 hydrogens and 6 oxygens. So how do you find the mass percent here? So let's start with the mass percent of carbon. So that becomes the number of moles of carbon times the molar mass of carbon over the mass of 1 mole of C6H12O6. So there are 3 things that we want to know. So notice that for 1 mole of glucose there is 6 moles of oxygen, 6 moles of carbon, 12 moles of hydrogen and 6 moles of oxygen. So this is the ratios that we are going to use in the formula. The other thing that we want to know is mass of 1 mole of C6H12O6. So now calculate the molar mass of C6H12O6. So the molar mass of C6H12O6. So the value is 6 times 12.01 plus 12 times 1.008 plus 6 times 16. So 6 times 12.01 gives you 72.06 plus 12 times 1.008, that gives you a value of 12.096 plus 12 times 1.08, so 6 times 16, so that is 96.00. So add everything up. So that gives you a value of 180.156. So notice that we need to have a total of 4 significant figures. So you have 180 point, if you round off 6 you get 6 here, so 5 becomes 6. So when you round off 6 again you get 180.2. So 180.2 gram per mole. So the molar mass, so the mass of 1 mole of carbon is 180.2 grams. Right, so 180.2 grams. Now the number of moles of carbon is 6 into the molar mass of carbon is 12.01. divided by the mass of 1 mole is 180.2 times 100. So when you calculate the value, so you have 6 times 12.01 over 180.2 times 100. So that gives you 39.988%. So we're close to 40%. Next, we want to find the mass percent of hydrogen. So that becomes the number of moles of hydrogen times the molar mass of hydrogen over the mass of 1 mole of glucose times 100. So that becomes 12. That's remember this, there are 12 moles of hydrogen. So 12 times 1.08, so from the periodic table, over 180.2 into 100. So you have 12 times 1.08 over 180.2 times 100. That gives you 6.7125%. So the maximum number of significant figures you want is 4, so this becomes 6.712%. Now, the next one is the mass of oxygen. So the mass percent of oxygen. So oxygen, there are 6 moles of oxygen times molar mass of oxygen is 16.00 over 180.2. So 6 times 16.0 over 180.2 into 100. So that gives you 53.274. So if you round it off, you get 53.27%. So in total, the mass percent of each of these elements. So let me write it as a small table. So element and the mass percent. So carbon, hydrogen and oxygen. Carbon has 39. So carbon in total has 39.988%. Hydrogen has a total of 6.712%, and oxygen has 53.27%. So if you end up adding all of them, you should get 100%. That's the idea behind the mass percent here. So this is in C6H12O6. So this is the problem. Now try an example. So try ammonium carbonate. So ammonium carbonate is NH4 taken twice CO3. So if you want to calculate try to calculate the mass percentage of each. I'm going to write all the atoms. So there is nitrogen, hydrogen, carbon and oxygen. There are 2 nitrogens, there is 8 hydrogens, there is 1 carbon and 3 oxygens. So try to find the molar mass of, try to find the compounds mass percentage. So if you want, I can write the molar mass of NH4 taken twice CO3. Ammonium carbonate is 80.05 grams per mole. So use the values. So pause the video right here and try to find the mass percentage of each of these elements. So now with the mass percent, one benefit of mass percent is it can help you calculate the amount of element for a given amount of mass. For example, if you take the formula mass of element times the present in the sample, so the mass of the particular element present in the sample can be given by the mass of the compound times the mass of element in 1 mole by the mass of 1 mole of the compound. So let's take a simple example of this. Let's take the same glucose example. They are asking you for the mass of carbon. So remember the formula: mass of element present in the sample is mass of compound times mass of element over the mass of compound. So you have a total of, so they are asking you for mass of carbon, can be given by the mass of glucose times the mass percentage of carbon in glucose. So the mass of glucose is 16.55 grams times the mass percentage of carbon, if you remember from the last problem, is 39.99%. So 39.99, remember percent, which means you have to write it by 100. So calculate the value. So you have 16.55 times 39.99 over 100. So that gives you 6.618 grams of carbon. So this is how mass percentage can be used. So mass of any element can be multiplied with the mass of the compound times the mass percentage in that compound. So this is the simplest formula that you can use. Next, let's go to empirical and molecular formulas. So what's the difference here? An empirical formula is the simplest formula for the compound that agrees with the elemental analysis. So it generally shows the lowest whole number of moles given and gives the relative number of atoms of each of the compound. For example, when you take hydrogen peroxide originally is H2O2, but the empirical formula is HO, which means that this is the minimal number of atoms that are needed to form that compound and agree with the elemental analysis. What is the molecular formula? Molecular formula is the one that shows the actual number of atoms in each element in a molecule or a compound. Right? So, for example, the molecular formula for hydrogen peroxide now becomes H2O2. So, you take out the common ones first. So, you bring it to the smallest number possible of each element. That is the empirical formula. And the molecular formula, we bring it to the molecule's actual identity. So, let's take an example. You have a sample of an unknown compound that contains 0.21 moles of zinc and 0.14 mole of phosphorus and 0.56 mole of oxygen. What is its empirical formula? So now let's try how to determine the empirical formula. So what are the steps that we need to use? First determine the mass in grams of each component element. Second, convert each mass that is in grams to amount in mole. So basically convert mass into mole and write a preliminary formula. Three, convert the amount mathematically to a whole number subscript. Right, so how do you convert this into the whole number subscript? Is generally by dividing each subscript with the smallest number. So out of all the numbers, choose the smallest subscript number and divide it using that number. And finally, if necessary, multiply a small integer to convert any decimals into integers. right? So this is the simplest way of doing it. So let's take a simple problem and let's try to do it. So notice that the first step is already done, which means that they are already converted into mass and also converted into mole. So they have given us the actual mole of each quantity. So what do you do here is write down the element symbols. So zinc is Zn, phosphorus is P, and oxygen is O. And under the subscript is under the number, write down the actual value of the number of moles. So 0.21, 0.14 and 0.56. So the first step is divide each subscript by the smallest subscript. So the smallest subscript here is 0.14, so divide it with that. So you have 0.21 by 0.14, phosphorus 0.14 by 0.14, oxygen 0.56 by 0.14. So cancel it out. So cancel it out, 0.14, this becomes 4 times, and when you cancel the first number, it is 1.5. So you end up with zinc 1.5, phosphorus 1, oxygen 4. Now notice that 1.5 is not a fraction. The smallest number that you can multiply to it to get into an integer is to multiply 2. So when you multiply 2, so now multiply 2 to everyone. So Zn 1.5 times 2, phosphorus 1 times 2, oxygen 4 times 2. So 1.5 times 2 gives you Zn3, phosphorus 2, oxygen 8. This is the empirical formula for the given compound, right? So hopefully the problem is clear. So let's try another example. So here you have analysis of an ionic compound, so that yields 2.82 grams of sodium, 4.35 grams of chlorine and 7.83 grams of oxygen. So they are asking you to find the empirical formula and name of the compound. So remember the first step, convert the mass into the number of moles. So now we have to find the number of moles of, so let me write as the simplest version, number of moles of sodium. That becomes the mass of sodium by the molar mass of sodium. So the mass of sodium is 2.82 grams. So 2.82 over the molar mass of sodium. If you take it from the periodic table, it is 22.99. So the value is 22.99. And when you calculate the value, so that becomes 0.123 mole of sodium. Next we want to find the number of moles of chlorine. So that becomes the mass of chlorine by the molar mass of chlorine. So mass of chlorine in the problem is 4.35 grams. So 4.35 over the molar mass of chlorine is 35.45. So when you calculate, total number of moles becomes 0.123 mole of chlorine. Next, number of moles of oxygen. So the mass of oxygen by the molar mass of oxygen. So the mass of oxygen here given is 7.83 grams over the molar mass of oxygen is 16.0. So that gives you a value of 0.489 mole of oxygen. So these are the final values that you have. Now what do you do in the next step? Write down the element and the number of moles in the subscript. So sodium 0.123, chlorine 0.123, oxygen 0.489. So in the next step, what do you do? Divide with the smallest one. The smallest one is 0.123, so you have sodium 0.123 by 0.123, chlorine 0.123 by 0.123, oxygen 0.489 by 0.123. So when you write down, you get sodium 1.00, chlorine 1.00, oxygen, you get a value of 3.98. Now 3.98 is nearly close to 4, so you can round it off. So round off all the values. So you get Na1, Cl1, O4. So this is the formula, or you can write it as NaClO4. So it is sodium perchlorate. If you remember from the last chapter, so the name is sodium perchlorate. So this is how you can start from mass and end up getting the final compound. Next let's try to find the molecular formula. So what we did now is try and find the empirical formula. So how do you find the molecular formula? Is just divide the molar mass of the given compound by the empirical formula mass, and you will get a whole number multiple. Multiply the whole number multiple to the empirical formula. That gives you the molecular formula. So the molecular formula is the whole number multiple of the empirical formula. So let's try this problem here. Notice that here initially all of them are in mass percent, so which means we have to calculate the mass of each of these compounds first. So let's try from mass. So mass of carbon is, they have given us the molar mass, remember that. So molar mass is 90.08 times the molecule, the mass percent 40 by 100. So that gives you a value of 40. So now let's try and calculate the mass of carbon. So you have 90.08 times 0.04. Sorry, 90.08 times 0.4. So that gives you a mass of 36.03 grams of carbon. Next, they are asking for mass of hydrogen, that is 6.71% mass percentage, that is 90.08 times 6.71% is 6.71 by 100. So that gives you a value of 90.08 times 0.0671. So the value is 6.044 grams of hydrogen. Next, finally, the mass of oxygen. So that is 90.08 times 53.3 divided by 100. So 90.08 times 0.533. So that gives you 48.01 grams of oxygen. So we have calculated all the values that we need. Next, let's calculate the value for the number of moles. So remember the calculation of number of moles. So the number of moles of carbon is the mass of carbon by the molar mass of carbon. So the mass of carbon here is 36.03 grams. So 36.03 divided by mass, the molar mass is 12.01. So that gives you a value of 3. So 36.03 over 12.01 gives you a value of 3. So this is the number of moles of carbon. Next, number of moles of hydrogen is the mass of hydrogen by the molar mass of hydrogen. So the mass of hydrogen is 6.044 divided by 1.08. You have 6.044 divided by 1.008. So that gives you a value of 5.996, which is nearly equal to 6. Next, number of molecules of oxygen is the mass of oxygen by the molar mass of oxygen. So the mass of oxygen is 48.01 divided by 16.00. So 48.01 divided by 16 gives you 3.00. So which is nearly equal to 3. Now write it as a subscript. We have carbon 3, hydrogen 6, oxygen 3. So the smallest number here is 3. So you get 3 by 3, hydrogen 6 by 3, oxygen 3 by 3. So 3, 3, 1, 3 ones, 3 twos, 3 ones. So you get C1H2O1. So this here is the empirical formula. So to find the molecular formula now, you need the whole number multiple. So the whole number multiple is the molar mass by the empirical formula mass. So we want to find the empirical formula mass. So empirical formula is C1H2O1. So that is 1 times carbon plus 2 times hydrogen plus 1 times oxygen. So that becomes 1 times 12.01 plus 2 times 1.008 plus 1 times 16.00. So you have 12.01 plus 2.016 plus 16.00. So that gives you a value of 30.03 grams. So molar mass is 90.08 over 30.03. So 90.08 divided by 30.03 gives you 2.999, so which is nearly equal to 3. So the whole number multiple is 3. So to find the molecular formula, so multiply the whole number multiple with each the molecular formula. So CH2O, so times the whole number multiple is 3. So that becomes C3H6O3. So this is the molecular formula, C3H6O3, and the empirical formula is C1H2O1. So this is how you can solve the problem and find your final answers. So let's try another example. So this time you try this example. So try these two problems. Here you have molar mass given. So molar mass is given and they have given us the mass percentage. So similar to the last problem. Next, in caffeine also you have the second problem, also you have the molar mass, and you have this time 4 elements. So mass percentages are given. So try to calculate from the. So try these two problems. So pause the video right here and try to calculate for these two problems. So the reason we don't use empirical formula more often is because compounds can have the same empirical formula but have different number of each of these in the molecular formula. For example, all of these compounds have the same empirical formula, CH2O, but every one of them has a different purpose and a different use, and also has a different structure as well. So which means that empirical formulas are not that useful in representing the structure, but they are useful in representing the actual mass of each individual element. Notice that all of these are multiples of each other, so they can be used as well, but the thing is they are not generally used as an empirical formulas themselves, cannot be used to represent the structures. The same thing happens when you have two molecular formulas with the same structure, but they can have the same properties. So for example, even two molecular formulas, even if you have a single molecular formula, two molecules with the same molecular formula can have two different properties as well. So molecules with different connectivity and the same molecular formula are called constitutional isomers. So remember the name, you're going to hear it again and again in organic chemistry. So whenever you see the term constitutional isomers, these are molecules with the same molecular formula, but the molecules are arranged, the atoms in themselves are arranged in a different order. For example, if you look at the carbons, notice the carbon arrangement is much more different in both the molecules. In the same way, in these two elements as well, the attachment of oxygen here is different in each of these elements, provided that's why you see there is a difference in their boiling points, their densities, their structural formula, and also their space filling models, even though their molecular molar mass stays the same. So this is why structures cannot be represented just by either the molecular formula or the general case of empirical formula. Empirical formula cannot be used to represent anything at all, but even molecular formula cannot also be used, because the main problem there is because of the presence of constitutional isomers having the same molecular formula but different connectivity between the molecules. So with that we end lecture 1.